Thank you so much, sir, for your outstanding introduction about me and giving me this opportunity to just give a talk in this international conference on multidisciplinary research in basic sciences at LCMDAV College, Kannur. Actually, I want to give a brief background about this talk. When Professor Chauhan he contacted me for this talk, he told that the listener will be students. So I asked him that what kind of talk should I give, and he explained to me that you should give them like a basic principles of nanotechnology, how what is nano, and how you are going to utilize the nanomaterials, how you are going to synthesize the nanomaterials, and how you are going to apply the nanomaterials for different applications. So, based on his recommendation, I prepared this talk. So, I am not sure if it is very basic for some of you. So, but anyway, I try to start from the basic to the real application of nanomaterials. So let us start with this. As Professor Chauhan he introduced me. My name is Ahmad Umar, and I'm leading a STEM Pioneers Training Lab, and also I'm serving as a professor in the Department of Chemistry, College of Science and Arts. Also, I'm a Deputy Director for Promising Center for Sensor and Electronic Devices at Najan University. So currently I am working as an adjunct professor at the Department of Material Science and Engineering at Ohio State University. So, as he recommended, as Professor Chauhan recommended, I'm just going to discuss about the advanced functional nanomaterials for environmental applications. So we are going to discuss about what is nano. Why nano is very important. This is a great question, that why nano is very important. So we will try to find out the answer in this presentation. Also we will discuss about the nanomaterials and type of nanomaterials and various properties of nanomaterials. And then we can go to the approaches, that how we can synthesize these nanomaterials. We will give some examples like zinc oxide, nickel oxide, tin oxide nanomaterials, and we will explore some applications, specifically the environmental remediation applications. So we are just going to discuss about zinc oxide, nickel oxide, tin oxide, and some composites also. We will also discuss about reduced graphene oxide-based composites, and finally we will just calculate and discuss about the future direction of nanoscience. So let us understand that what is nano. Actually, nano, there is a confusion among people that what is nano. Nano is nothing but a dimension. It is just a dimension. So it is derived from a Greek word called nano. If you are talking about the weight, it can be a nanogram or whatever. So it is just dimension. If you have a different dimension, you can just add nano. So nano, once you add the nano, it will be like 10 power minus 9 for that that measurement. So you can see that this is the smallest which we can see in a ruler, and it is 1 million times smaller than the smallest measurement we can see on the ruler. So nano is very, very small. It is the 1 billionth part of a meter. If you just see the dimension, then it is a 1 billionth part of a meter. So it is like 10 power minus 9 nanometer. To understand it better, we can have the comparative dimensions. Like for example, a common person, his height and his dimension is about 100. His height is about 180 centimeters. So which is around 2 billion nanometer. A person who is about 180 centimeters is about 202 billion nanometer. And the apple size is about 80 million nanometer. The ant, which is very small, which is about 5 centimeters. In nano dimension, it is about 5 million nanometer. Similar to like human hair, it is about 80,000 nanometers. And the smallest thing we can see through our naked eyes is about 10,000 nanometers. The E. coli bacteria size is about 2000 nanometers. Cellulose nanofibrils is about 3.5 to 100 nanometers. DNA size is about 2 nanometers. And hydrogen atom size is about 0.1 nanometer. So this is the comparative dimension of nanometers. Now you see the human red blood cells is about 7,000 nanometer wide, and if you just combine four molecules of water, it will be 1 nanometer wide. So you can also understand that our fingernail grow like 1 nanometer per second. So this is like a comparative dimension for nanometer. Also, nano system exists deeply in the nature. For example, if you go to a small part of the skin, like 10 centimeter skin, if you go deeper and deeper and you try to explore this in high resolution, you will find that you can reach to like 10 micron and it will be white blood cells. So when you go to 100 nanometers, you can see this DNA structure. And 10 nanometers, you can fully understand and see the helical structure of DNA. And when you go deeper, you can see the 1 nanometer atom inside the DNA. So this is the nanosystem is already exist in the nature. Now, I will give you some examples that how the nanosystems exist in the nature. Like I just took some examples, 3-4 examples from the nature. Like if you see the gecko, it climb on a glass wall, it climb on any surface, it never fall. So people were trying to understand that why this gecko can climb on a wall or any surface, like even glass surface, which is very difficult to climb. So they examined and they found that this gecko food is made of spatula. That is spatula, and each foot of gecko has around 1 billion spatula, which create an intermolecular force between the surface and the food and make a strong bonding with the surface. So this is the reason, and you will be surprised to understand that gecko can lift up to 130 kilogram weight, so which is very high. Based on this observation, the scientists developed a very high class adhesive, and it is already available in the market. I can give you some examples also, like from the nature peacock. If you see the peacock has a very very good examples from the nature, because the peacock feathers, if you see from different directions, you can feel that it shows different colors, which is because of the nanoparticles over the surface of the feather. And this feather has a different wavelength, and when the light is coming from different direction, it shows different colors. So this is one of the examples in feather. And those feathers have photonic crystals. Also, these feathers, the peacock feathers, they have the hydrophobic surface on the nanohydrophobic surface on this nanophotonic crystal. So once there is a water on this feather, it cannot stuck on the feather. Similarly to the butterflies, these also have the similar kind of characteristic like the feathers of peacock, and it also shows different kind of colors on their skin. So this is some of the biomimicry examples, like this lotus leaves. They have hydrophobic surfaces and dust repellent surfaces. So because the people scientists they develop dust repellent paints and hydrophobic paints based on that concept. Like a gecko, I mentioned in the gecko, they develop a very good adhesive for that. And different kind of different kind of biomimicry is available in the nature, and the scientists, they just took the concept from there and they developed a different kind of product based on that. So the question, now we understood that what is nano. Nano is just a dimension and nothing else, and if we and it is a measuring dimension. So when we have any like unit, we can just add the nano and it will be in that. So why nano matters? One of the most important characteristics of nano is the surface area. So if we have a very high surface to volume ratio of any material, we have very high surface for the reactivity because we have a very high surface open for different interaction, different molecular interaction. So for example, like we have one bulk material and we just divided it in nano size. So the size of the material is the same, but we got a very high surface to volume ratio. This high surface to volume ratio is sometimes change the properties of material completely from their bulk counterparts. So this is the beauty of nano. One of the most important characteristic of nano is the high surface to volume ratio. So we can give you an example, like for example, you have one cube which is about 1 centimeter by 1 centimeter, and the total surface area of that cube is about 6 centimeters square. So if you cut that cube in like 1 millimeter cube dimensions, then you are going to increase the surface area of your material, which is 1 centimeter by 1 centimeter, and now you are cutting the cube in smaller pieces like 1 millimeter cubes. You are increasing directly the surface area from 6 centimeters square to 60 centimeters square. Another way that if you increase, if you just reduce the size of your cubes from 1 millimeter to 1 nanometer, then you can increase the surface area about 60 million centimeters square, which is huge, very huge. And because of this high surface to volume ratio, the reactivity and interaction of on the surfaces of these nanomaterials is increased with other materials. So this is one of the most important characteristics of nanomaterials. That why nanomaterials is very important, because they have a very high surface to volume ratio. Because of high surface to volume ratio, they can show different properties, which is very different from their counterparts. So there is one more important thing which I wanted to emphasize, that nanomaterial is the material which is in the size from 1 nanometer to 100 nanometer. More than that, if you have any material which is more than 100 nanometer, it is called micromaterials. So nanomaterials is just a material which is in the dimension of 1 to 100 nanometer. And by the way, we can engineer the nanomaterials in a way which we want, and we can utilize those for application. Like we can control the morphology dimension. There are so many kinds of nanomaterials which we can synthesize, but based on dimension, we can understand the types of nanomaterials. So based on dimension, we can have like 4 kind of nanomaterials, like 0 dimensional, 1 dimensional, 2 dimensional, and 3 dimensional nanomaterials. So in 1 dimensional nanomaterials, any material which is grown in zero direction, there is no direction for that material. It's called a 0 dimensional nanomaterial, such as nanoparticle, quantum particle, and so on. So any material which is in no direction, it is called 0 dimensional. And a material which is grown in a single direction, like for example, other crystal faces are suppressed and it grows in a single direction, it is called 1 dimensional nanomaterial. So it is like a nanotube, nanorod, wire or so on, and fibers and so on. So another type of material is the two-dimensional nanomaterial. If any material is grown in two-directional, like for example in two-directional and two crystal phases, it means that it has a two-dimensional nanomaterial. And three-dimensional nanomaterial is the material which is grown in a three-dimensional morphology. It is called three-dimensional, such as like nanoballs, core-shell structures, arch-like structures, and so on, like different hierarchical structures. It is all three-dimensional nanomaterial which is grown in different directions. So also we can understand that nanomaterials are not like only one kind of nanomaterials. Any nanomaterial has a different kind of there are various kinds of nanomaterials, such as like carbon nanomaterials, inorganic nanomaterials, some organic nanomaterials also we have, hybrid nanomaterials we have, and there are so many other techniques, so many techniques by which we can synthesize the nanomaterials. So we can utilize these nanomaterials for different applications, and we are going to just discuss those applications in the coming slides. Here there is we need to understand one more thing, that there is a difference between nanoscience and nanotechnology. So what is the difference in nanoscience and nanotechnology? Where nanoscience is the science where we study about the growth properties and characteristics of nanomaterial. So we are trying to understand why in nanoscience, like this is a journey. Nanoscience to nanotechnology is a journey from why to how. It means that in nanoscience we are just going to understand that how why the nanomaterials have specific properties. Why we will have the nanomaterials of a specific material. For example, if we grow the nanomaterial of any specific material, and we utilize that nanomaterial for a specific application, then it is a technology. Once we applied our why to how, it is a technology. So we are going to have the nanoscience. Nanoscience is a science in which we study about the properties and different characteristics of nanomaterials, like how we are going to synthesize and understand the characteristic of nanomaterial, and then how we are going to utilize that nanomaterial for some specific device applications. This is a technology. So this is a bridge between the science to the engineering. Once we utilize the nanomaterial for a specific application or any application, it is called nanotechnology. So like, for example, we have the nanowire and we are going to make the transistors, a single nanowire based transistors, then it is a nanoscience and it is a nanotechnology. Like we have nanoparticle of silver oxide, a silver nanoparticle, and we are just going to utilize the silver nanoparticles for some applications. So it is like nanotechnology. Now we understood that what is nano, and we understood that what is nanomaterials, why it is important, what are the characteristics of nanomaterials, what are the properties and like characteristics of nanomaterials. Now we need to understand that how we can synthesize these nanomaterials. So there are two main approaches to synthesize these nanomaterials. One is the top-down approach and another is the bottom-up approach. So in the top-down approach, we have the bulk material. Okay, we are going to have the bulk material and we are going to make it to nano. So how we are going to make the bulk material to nano? By slicing or successive cutting of this bulk material until we reach to the nano level. So this is in the top down, we have the bulk on the top, and then we are going to the down and reaching to until nano. So this is like there are different techniques for this top-down approaches. Like we can have the mechanical. There are several mechanical methods like cutting, etching, grinding, ball milling, and also in the lithography process like photolithography, electron beam lithography. So these are all other techniques in which we can achieve the nano from the bulk. There are another technique which is like bottom-up technique, which is very famous and widely used technique. Like most of the people, they use this bottom-up approach because the top-down approach is like relatively very expensive because most of the techniques used for top-down approaches are very expensive. So normally people use to synthesize or to prepare the nanomaterial this bottom-up approach. In this bottom-up approach, like we are building the material from atom to atom and molecule by molecule. So this is like we are starting from the atom to atom and molecule to molecule until we reach to the nano. So we build the material by atom and molecule by molecule. And then this atom by atom deposition or molecule by molecule deposition leads the formation of clusters, and these clusters are finally merge each other and make the nanoparticles. So this is the basic concept of bottom-up approach. Like we are starting from atom to atom and molecule to molecule until we reach the nano. So there are so many techniques for bottom-up approaches like physical technique and chemical technique. These are two categories for bottom-up approaches. In this physical and chemical techniques, there are so many other techniques like, for example, evaporation technique, sprouting technique, plasma technique, laser ablation, and so on. Also in the chemical techniques, we have the chemical vapor deposition, we have the hydrothermal deposition, pyrolysis, and solvothermal, and so on. There are so many other techniques in this chemical technique, like solution method and room temperature synthesis, and so on. So any technique which leads the formation of nanomaterials by assembling the atom to atom and molecule to molecule and cluster to the nano particle or nanomaterial is called the bottom-up approach. These are two different approaches. So once we have the nanomaterial, what we are going to do, how we are going to characterize. So this slide will give you a glimpse that how we are going to characterize the nanomaterial. So if you want to check the morphology of your nanomaterial, you can go for field emission scanning electron microscopy and transmission electron microscopy. And if you want to check the crystal structure and different crystal patterns in your material, you can go for X-ray diffraction. The thermal properties can be understood by TGA, thermogravimetric analysis, and optical properties can be examined by Raman scattering and photoluminescence, UV luminescence, and so on. The structural and compositional properties you can understand by Fourier transform infrared spectroscopy and energy dispersive spectroscopy. And also you can check the elemental analysis, elemental composition by elemental mapping, elemental analysis. So we can utilize different materials, different nanomaterials for different applications. Like we can use those nanomaterials for sensor applications, photovoltaic applications, photocatalysis applications, some agricultural applications, quantum technology, biological applications, nanoelectronics, optoelectronics, and so many other medical applications. So there are so many applications and so many techniques, so many characterizations. I will give you some examples that how ball milling is. I just choose two examples in each section, like the top-down approach and bottom-up approach. So in the top-down, I will give you one example of ball milling. That this is you have a bulk material and you want to make it particle of the size of the material. So this is like putting your material in this ball milling and grind that material and each the size reach to the limit. So in the ball milling you have different grinding balls, different size of grinding balls. So if you want to make material in very fine material and in nano size, then you need to choose the smaller balls. So this is like a basic concept of making the nanomaterials using the top-down approach. This ball milling, it deforms the structures, it breaks the structures and make the supplementary reactions and reduce the size of the material by grinding the material to the nanoscale. There is another technique is the lithography technique. We had one patent on that lithography technique, and what we did, we had a film, silicon film, and we deposited on the silicon film with some specific thickness of metal film, and we just make the plasma treatment of that metal and make the droplets on the film. So after we made the droplet, we defined the diameter of the nanomaterial. So this droplet was the key to define the dimension of the nanowire which we made. So what we did, we just make the droplets over the surface of the thin film, and we just etch the film like we did etching. You see, dry etching, and this droplet was making as a reference for the diameter of the nanowire. So we got very well aligned nanowire with droplet. Why this droplet? Because this droplet can work as an electrode in the device fabrication. So we made like nanowire, single nanowire, and we just with electrode. So it is a very good discovery, and we just got patent on that discovery. So we can go on bottom-up approach. I'm going to give you two examples of the techniques which we used to synthesize the nanomaterials. Like one is the evaporation method, like thermal evaporation method, and another is hydrothermal or solvothermal process. So we are going to discuss about the evaporation process. This is a simple process. In this process, we have a horizontal quartz furnace. Maybe physics guys they knew that this is like a simple setup to synthesize the nanomaterial. We have like the horizontal quartz furnace. We have the source powder, like in case of zinc oxide, we have zinc powder. And then we put different substrate adjacent to this zinc powder, which is in the board, and we just heated this. So, what is happening during the reaction? That at the same time we are introducing nitrogen and oxygen gases inside this furnace. Why nitrogen and oxygen gases? Because we want to create an inert atmosphere inside the furnace, and also we need to provide the oxygen so that we have the zinc powder, and when it reacts with the oxygen, it can convert to zinc oxide. So during this reaction, like we can heat our zinc powder more than the evaporation temperature of zinc powder. So once we increase the temperature and heat the zinc powder, it just go and evaporate and make the vapor, zinc vapor, which react with oxygen and condense on the lower temperature region, and just condense on the substrates. So it deposited on the substrate. So zinc oxide is made in the air and deposited on the substrate, and finally we are getting the zinc oxide on the surface of this substrate. So you can have different kind of substrates. We can discuss later on. that we can have different substrates, like for example silicon substrate, glass substrate, or whatever substrate, depending on the temperature which you are going to use for the synthesis of this material. So I will show you that how the temperature also affect. There are so many parameters which are affecting the final product, like morphology and crystallinity and the characteristic of your nanomaterial. There are several parameters. So, like for example, the substrate has a very huge impact on the morphology and properties of nanomaterials. Also, the source material in case of zinc oxide, zinc powder, zinc acetate, zinc chloride, etc. So I am just giving you one or two examples in each cases just to cover all the lecture. And also we have different substrates like silicon substrate, silicon different orientation substrate, gallium nitride substrate, stellolite substrate, and so many other substrates. Also we have gas pretreatments during synthesis. These all factors, and there are so many other factors, are affecting the final product of your nanomaterial, like the properties and the morphology and the size. There are so many other characteristics of your material. So to synthesize the nanomaterial, you need to be very careful to make an appropriate process parameters to get the desired nanomaterial for this specific application. So here, if you see that we have a different substrate, like one substrate, two substrates, three substrates. If you just assign it A, B, C, like A, when you go away from the center of the heating zone, you can find like different temperature zones for different substrates. So you see, on the higher temperature, we are getting this kind of morphology, like this arching-like structures, which is composed of different aligned nanowires and make these arching-like structures. So in another in another region, like B region B, which has a temperature about 525 to 490 degrees centigrade, we are getting these snail-like structures, which is also composed in arching-like morphologies. And when we go to section C, like temperature zone C, which is like about 490 to 440 degrees centigrade, we are getting also we are getting like a nail-like structure, but the composition is not the structure is not that accurate as we see at position B. So this is because of the zinc distribution. We just simulated and we found that once we increase the distance between the center of the furnace to the substrate, the distribution of zinc is reduced. Like the zinc concentration is reduced. Because of the zinc concentration, we are getting this kind of morphology. So there are other parameters also. We did some other parameters, like we did some hydrogen treatment, and we found that if you do the hydrogen treatment, you are getting a fine nanomaterials. So which is very important, because hydrogen is a reducing gas, and when you enter hydrogen in your furnace, the nanostructures are getting sharper and better morphology compared to when without hydrogen treatment. And there is the effect of time also. This is very important parameter that the time has a very huge impact on the morphology of your nanomaterial. So we got we did different experiments, and we found that with time, you can see the deviation and growth. So at 7 minutes, we got little bit growth on the surface of our nuclei. These balls are act as nuclei, and then each ball is nucleated on their outer surface and form this arch-like structures or flower, non-flower-like structure on the surface of silicon substrate. Also, we have like three-dimensional nanomaterials. We got by six-fold symmetrical hierarchical zinc oxide nanostructures. In this case, we used a very specific technique to grow these nanomaterials. Basically, the zinc, the crystal structure of zinc is hexagonal. So, what we did, we just control the nucleation on each surface of our nanowire, and we got this kind of morphology finally, which is grown on silicon substrate. So these are all are like different nanomaterials which was prepared in our group. So we also utilize our like nanowires to make the devices, like single nanowire based devices. What we did, we have the prefabricated electrodes like on the silicon oxide silicon substrate, and we just aligned our zinc oxide nanowires and we checked the electrical properties, which was very efficient, very good electrical properties we got using this transistor. So we can go, now we can discuss about the other technique, which is like hydrothermal solvent process. And this is also in the bottom-up approach. So we are taking two examples in each processes. So in this process, this is a very versatile technique actually to synthesize the nanomaterial. In this technique, there are two processes, like one is the hydrothermal process and one is the solvent-thermal process. Both the processes are same, except when we are using the hydro, means like water as a solvent, then we call it a hydrothermal process. And when we are using non-aqueous solvents, like some chemicals, non-aqueous solvents, then we call it as solvent-thermal process. So both processes are same, except the solution which we are going to use. Like for example, in aqueous solution, it is called hydrothermal, and in non-aqueous solution it is called solvent-thermal. But the instrument which we are going to use in this synthesis is the same. So this hydrothermal is a very versatile technique because it has a huge strength. Like it is a one-step process, and we can have the less energy consumption. It is a closed system, it is not open system, it is closed system. So because of the closed system, it has a very low impact on the environment. And we can get the material which we are synthesizing with very high homogeneity than solid state processing. So this is a very versatile technique. In this is a very easy technique. Like we have there are different kind of hydrothermal reactors in the market. I just put 2-3 types. So normally people are using this kind of hydrothermal reactors. And they have the Teflon beaker which is capped, and then they have a stainless steel chamber. So we put our material in this Teflon beaker, we pack it, and we just place this Teflon beaker inside this stainless steel chamber, and we just close and heat it for a specific temperature, a specific time, and finally we get the product. So this is a quite easy and one-step process. Because of this, most of the people are using this hydrothermal process to synthesize their material. But in this hydrothermal process also, there are several parameters which affect the morphology and properties of your nanomaterial. Like for example, surfactants, like reaction time, your source material, what kind of source material you are going to use to synthesize your material, the reaction temperature, reaction time, the concentration of the precursors, effect of pH. But most of some of the most important parameters are the pH, effective pH on the morphology, and the reaction temperature at time. These three are very important. So we can I can give you some examples, like few examples for that. For example, we synthesize some manganese oxide nanomaterials, and we use them for